Hi guys, we're going to be going over chapter 18, which is section 1, and it's not going to be a whole lot of information from this chapter. We're going to keep zooming along. So get your notes ready there for magnets and magnetism. And like usual, just highlight and write things down along the way if you don't have them written down. So first things first, we all know we've probably played with magnets in our life. So it's any material that attracts iron or materials that contain iron. And there are always two poles. So that's important to note, and we'll be talking about that. So they exert forces on each other, and they are surrounded by a magnetic pole. So what is the magnetic pole? These are one of 2 points, such as the ends of the magnet, that have opposing magnetic qualities. So if you can look at this picture here that I pasted in, you can see there's a north, which is the red, and a south, which is the silver. So as you can see on the ends there, more of those paper clips are sticking on the ends because they're the magnetic effects are going to be the strongest on the ends there. So you can kind of see that in that picture. So if we hang a magnet, one end always points north, and that would be what we call the magnetic north pole. So the opposite end points to the south, which we know is the magnetic south pole. So all magnets will have a north and a south, and we'll talk about what that looks like if we cut a magnet in a minute. But what is magnetic force? So there's an area, right, that those magnets are going to have a force of attraction or repulsion that is going to be generated by moving or spinning electric charges. So think of it as an area. So if you look at the magnetic force between magnets here, if we try to put two north, right, in that first picture together, they're going to repel. In the middle here, if we're trying to have two south parts, they're going to repel as well. But then if you match up a north and a south, they're going to end up being attracted. So think about back to the example I've used before with like the trains that you may have played with when you were little. Sometimes it would repel if it was the two souths or the two norths, and then of course it would connect together when you hit the north and the south. So that's a simple example. When you have a magnetic field, there's an area or region around the magnet where those forces can act. Obviously, if they're too far apart, that's not going to work. So whether something is magnetic or not really depends on what those atoms look like. So as the electrons move around, they make or induce that magnetic field. Then, of course, then we have an atom with a north and a south pole. So in most materials like copper and aluminum, the magnetic fields of each are going to cancel each other out. So they're not going to be magnetic. But iron, nickel, cobalt, those atoms of those elements are going to have tiny areas that we call domains. So these line up and make the strong magnetic force, the strong magnetic field that we know of having the magnets and playing with them. So the arrangement of those domains determines whether it's a magnet or not. How are they arranged? So if you take a look at this picture, that gives you kind of an example. So on the left, if the domains of an object are randomly arranged, the fields of the individual domains are going to cancel each other out. So no magnetic properties. On the right, if most of the domains in an object are aligned, so you can see in the picture they're kind of lined up there, and that's going to cause those magnetic fields of those individual domains to combine, right? So the whole thing will be magnetic. So that's a good example there. So they may not always stay lined up, and so magnets can actually become what we call demagnetized. So we call that process demagnetization. So there are permanent and temporary magnets, in other words. So if something gets really hot, that can actually cause a magnet to be demagnetized. So we can also magnetize things like nails. So we can make sure that they are magnetized, and we can line up the domains. So one of the things I always mention is if you've ever noticed or watched roofers roof a house, you'll know that they sometimes have to take off the old shingles, which have a ton of nails in them. And you always want to, when you roof a house, use magnetized nails because they fall into the yard, and you can just take a giant magnet and roll it around the lawn and pick up all those nails so they don't end up in tires or in your yard and on your driveway and stuff like that. So obviously they try to clean everything up, but they just take a giant magnet and move it across the lawn when they take those old nails out of the roof. So we can magnetize objects, as I said, and so we want to with nails. So what happens if we cut the south end off of a magnet? Think about that for a second. So you have a north and a south. What if we were able to cut the south off? What happens? Well, as you read in your book, what happens is there becomes a new north and south. So if you look at this, say we were to cut this right down the middle, we have two magnets now that have their own north and south. And then we can keep doing that, right? So they're just showing you that in that picture. So we have two types of magnets that we want to just kind of go over here. We have what are called ferromagnets. These are going to be made of iron, nickel, cobalt. These are really strong magnets, okay? Then we have electromagnets made of with electric current. So they usually have an iron core to them. So, might not have thought about this, but the Earth is a giant magnet, right? So don't get the magnetic north and south poles confused with the geographic north and south poles. Sometimes people do that. So when we talk about geography, this picture is really helpful. Here's the geographic North Pole right here and the geographic South Pole right here. Now you'll notice the magnetic poles are a little bit different. So here is the magnetic north, and then moving across here is the magnetic south. So they are not the same thing. So remember, the geographic poles are on the axis that the Earth rotates on. And the magnetic poles are on the points on the Earth's surface where its magnetic forces are going to be really strong, right? So the magnetic field, those lines around the Earth are similar to the magnetic field lines around a bar magnet. So it's kind of like on a different scale, right? So this is a good picture to take a look at. They're not the same thing. That's a big piece of science we want to make sure we understand. So scientists think that the Earth's magnetic field, it was made by the movement of the electric charges in the core, right? Remember, the core of the Earth is made of nickel and iron. So as the Earth rotates, the liquid in the core rotates and charges move, all right? So then we have, obviously, a magnetic field. So that's kind of interesting to think about. Now, I think I've mentioned the northern and southern lights before, but it's always good to go over those again. We call those in science auroras, right? So they compare them to a curtain of light in the sky. So there's gases in the atmosphere, which we've discussed before, and they have charged particles from the sun. And so they are obviously in the north and in the south of the geographic Earth, right? So the aurora borealis we can see up in northern Wisconsin. Sometimes, very rarely, we can see it here, but that would be the aurora borealis, and then the aurora australis, clearly down in the southern part of the Earth, is the southern light. So you can kind of see a picture. This is not the best picture. It's one that I found in your book, but there are really great pictures that you can take on your own if you ever get to see them, or that you would be able to maybe find on Google. So that is magnets. And hopefully you took good notes. You can go back if you need to, but that is the basics.